Standard calculus works perfectly when everything happens along a straight line, but physical engineering requires us to analyze objects moving through three-dimensional space, navigating curves, twists, and uneven terrain. To calculate physics here, we need a mathematical upgrade. This chart shows a standard definite integral. It calculates the net area under the curve y equals x squared from 0 to 2. You accumulate a specific quantity, represented by the blue shaded region, along a straight interval on the flat x-axis. This basic approach stops working when we model real-world physics. Particles traveling through a magnetic field or vehicles navigating a mountain road do not travel along a single straight axis. They move along curved paths through complex environments. Look at the right side of this diagram, showing a curved 3D surface projecting down to a path C. This scalar line integral calculates the area of a winding curtain dropping from a surface in space down to a curved base path. Switching from a static surface to an active environment, we use a vector line integral. This measures the total work done by a force, like gravity or a fluid current, pushing an object along a specific path. We find this by taking the dot product between the field's vector and the path's directional tangent vector at every point. Both methods share the same underlying mechanism. They take a complicated three-dimensional journey and mathematically flatten it into a single variable equation that we can easily solve. Let's apply this to a physical object. We need to find the total mass of a helical spring that has a variable density. We map its shape in space using these three parametric equations: x equals 2 cosine t, y equals t, and z equals 2 sine t. To calculate mass, we must isolate the scalar differential element, known as ds. We do this by finding the magnitude of the path's velocity vector. We take the derivatives of our parametric equations, square them, add them together, and simplify. The entire physical curve translates into a simple multiple, the square root of 5 dt. Next, we replace the variable density with its exact position along the curve. The density formula is 2y, and since our parameter for y is t, we substitute 2t. We define our full path from 0 to 6 pi, resulting in a standard, clean, one-dimensional integral. Evaluating this gives us a total mass of 36 pi squared times the square root of 5. By parametrizing the position equations, we translated a tangible 3D object into a calculable format. Now let's calculate the total work done on an object traveling straight through an active force field. The target object moves along a rigid line segment from coordinates 1, 1, 1 to 2, 3, -1 against a vector field defined as y, x, 4. We parameterize the linear path to create our position vector, r of t. This gives us discrete equations for x, y, and z in terms of t. Taking their derivatives produces our exact vector differential elements, dx, dy, and dz. Because this is a vector field, we compute the dot product between the force field and our movement vector. This expands out to y dx plus x dy plus 4 dz. We swap every single spatial variable for its exact t equivalent from step 1. The terms combine and simplify beautifully into the expression 4t minus 5. We integrate this simplified expression from 0 to 1. The final calculation yields a value of -3. Notice the difference in mechanics here. While the scalar ds relies on the absolute magnitude of velocity, the vector dr requires the dot product. A vector integral must account for the specific direction of your movement, either with or against the surrounding field. Whether calculating mass along a twisted wire or measuring fluid resistance across a straight pipe, every line integral follows a strict 4-step methodology. Step 1. Parameterize your path for integration limits. Step 2. Select the differential, magnitude formula for scalar ds or dot product for vector dr. Step 3. Substitute spatial variables entirely into the t-domain. Step 4. Evaluate the standard definite integral. Line integrals act as direct translation tools. By isolating the path and defining movement through time, engineers can decode complex multidimensional physics into manageable single-variable math.